Hello, welcome to the next lecture. So this one is all about probably the ultimate geohazard, which are impact events. And here we're talking about our planet essentially being impacted by large rocky objects from space. Let's call them asteroids. So these asteroids we know travel through space at a velocity of something like 4 times the speed of a speeding bullet. So we're talking 20 kilometers per second or more. And when they have large enough mass, that a body like that, when it strikes the ground, releases huge astronomical amounts of energy, much larger than any other geohazard that we're looking at, like volcanic eruptions um, or earthquakes. So in this lecture, we're going to learn about, should we be scared? um, will it happen in my lifetime, etc. So what's the likelihood of these impact events happening? How often do they occur? What's their recurrence interval? On average, how often do they happen? Is there ways of determining that from the past, from the geologic past? And we'll think about at the end, will we think about mitigation? Like all hazards, we have to think about sort of mitigation efforts. Can you mitigate the impact of an asteroid? Can you, risk mitigation, the process of reducing risk exposure? Can you reduce the risk exposure, and can you minimize the likelihood of an incident? I'll only give you one option at the moment, at this point. That's if anyone's seen the movie Armageddon. Do we have Bruce Willis at hand to send up there, land on the incoming asteroid, blow up, drill a hole, throw a nuke down it, and blow it up, and blow it up into several pieces? Will that work? Would that work? What is there any other options we have? Well, we'll find out at the end of this talk. All right, so impact events. Do they really happen, first of all? Well, they do. So I'm going to go through a few examples during this talk. So, for example, we'll be talking a little bit about with some images what happened back in 1994, which is when a comet struck the planet of Jupiter in our solar system. They've named this comet the Shoemaker-Levy comet, and yeah, we saw it in real time. It's the only observed impact in our solar system actually recorded and seen in real time. We'll be talking about historic events. What's called the Tunguska event happened in Siberia in 1908. We'll be talking about possibilities of very large impacts on Earth and evidence for such as Meteor Crater in Arizona, which is the site of an impact event 50,000 years ago. And now, in fact, we found around about 150 craters, actually probably a little bit more than that now, have been identified on Earth. But most of those we'll see are not visible on the surface. Most of them happened a long time ago. We're talking about millions of years ago. And they're kind of underlain by other rocks, other sedimentation now. With that note, partly actually, so we'll answer the question I'll ask you now to think about. So, okay, we have Meteor Crater there on Earth, but there aren't actually many more examples of craters that look like a crater on planet Earth. But look at our nearest neighbor, the moon, not very far away. It's littered with craters everywhere. You can look up. You can even see some of them, on with a naked eye on a full moon. But certainly with a telescope, you will see literally thousands of small and large craters pockmarking the whole of the surface of the moon. Okay, here's the Earth. There's the moon. We're not far apart. Why the difference? Why do we have so many craters on the moon but not the Earth? One would think we're a larger object, would have just as many, just a higher concentration of them. So why the difference? I'll just give you a moment to think about that. Well, there's a couple of reasons, or possible reasons. First of all, which is, if I ask this in class, most people say, shooting stars, they're burnt up in the atmosphere, and that does happen. Yes, smaller objects, incoming objects, are burnt up in our atmosphere. The moon doesn't have an atmosphere, therefore they reach the surface. But that's only the very small objects, incoming meteors, essentially. What about larger objects which can pass through our atmosphere, which, and produce these large craters we see on the moon? Why don't we have the craters here? Well, it's all to do with the difference. The Earth has weather. It has the water cycle, the hydrologic cycle. It has processes of weathering and erosion, Earth surface processes. The moon does not. It doesn't have those active Earth surface processes. So once an impact event, it stays there. It's kind of fossilized. It stays there as a feature on the surface. The Earth, things are weathered, things are eroded, constant change, constant sedimentation. As I said, many of these older discovered impact sites have been buried essentially by more and more sedimentation and deposits of sediment and rock eventually. So they're not visible on the surface now. So that's the reason. But if you look at the moon, it gives you a clue as to how often these things happened. And you'd think, hey, there's a lot of craters on the moon. It's happened a lot. And you'd actually be right in thinking that. But saying that, most of these impact craters on the moon happened in the early solar system, or the early stages of the Earth-Moon's kind of history. So we're talking several billion years ago. But we still have many, many recent craters also on the moon. All right, so let's define some words, because we're going to mention these throughout. So as far as this object, the general catch-all, which isn't on this list actually, I'll mention in a later slide, for these objects is bolide, B-O-L-I-D-E. But the ones here, it said asteroids, meteoroids, and comets. So how do you classify these different labels? So particles in the solar system are arranged by the diameter, how big it is, and what it's composed of, what it's made of. So the big rocky thing, well, the rocky material essentially, you either have the larger asteroids, which as we'll see are kind of larger than 10 meters in diameter, and less than 10 meters in diameter, we call them meteoroids, or meteoroids. Hard word to say that, isn't it? And these originate from the asteroid belt, which is located between Mars and Jupiter. It's kept in that orbit because of the huge gravitational attraction of Jupiter, we think, but it's basically the aftermath, what's left over from the creation of our solar system. And these are composed of different types of asteroids, generally rocky material. Sometimes you can get more metallic asteroids and meteoroids, and also sometimes a mixture of rocky metallic, a mixture of material. Comets, and we'll say a bit more about both in a little while. Comets originate from way out in the solar system, past Neptune, in what's called the Kuiper belt and the Oort cloud. These are composed largely of frozen gases, gases like methane and carbon dioxide. And these are these icy, often called dirty snowballs, because they kind of have bits of rocky material kind of embedded in the ice. These sometimes everything, all these objects orbit the sun, but sometimes they do come close to Earth's orbit. Okay, so let's start off looking at a bit more detail in asteroids, or a few more facts. They range in size. As I say, they're the larger of the rocky objects. They range in size from about 10 meters, or 30 feet, to 1,000 kilometers, or 620 miles. The largest known asteroid is 620 miles in diameter. Most lie between Mars and Jupiter in the asteroid belt. Small bodies, relatively compared to planets, but the largest, Ceres, is the one I mentioned, is about 620 miles in diameter. Some, though, have very eccentric orbits. They don't have the nice kind of circular, if you will, orbit of the asteroid belt. Some of them are more eccentric, more elliptical. So that can take them, and because of that, we'll see on the next slide in a diagram, they can take them out of the general orbit of the asteroid belt and cross the orbit of other planets, including the Earth. Many of the recent impacts on the Moon and Earth were collisions with these asteroids. They're often of a regular shape. They're not nice spheres. Sometimes almost like potato shaped. And as I said earlier, most are thought to be the leftover rocky and metallic debris from the solar nebula as it was forming in the creation of the solar system. So it was 4 to 5 billion years ago. And what was left over kind of concentrate itself in this orbit of where the asteroid belt is located between Mars and Jupiter. Okay, the asteroid belt. This is about geohazards. This is about those asteroids which don't nicely stay in their orbit in the asteroid belt. These are the ones with the eccentric orbits which can theoretically, or the small probability of them crossing our orbit, and there's therefore a small probability if they both come to the same point, they can impact Earth. So here it says the orbits of most asteroids lie between Mars and Jupiter. Also shown are the orbits of a few known in the red lines near-Earth asteroids, or just shortened to NEAs, so near-Earth asteroids. Perhaps, as of 2021, 10,000 potentially hazardous asteroids with near-Earth orbits have been discovered and tracked by NASA mainly. So we see potentially hazards. Generally, they say around about over 140 meters in diameter. The larger ones, which is the first ones they started to track, ones over 1 kilometer in diameter, we've pretty much identified everything, all the ones which have possible near-Earth orbits, and there's about 900 of them, of these larger ones. But you can see in the red lines occasionally these eccentric orbits, more elliptical, that there is a very small chance of them striking Earth. But remember, there's a lot of space out there. It's still very, very small probabilities. Oops. Okay, so meteoroids, which are the smaller rocky material, these range in size from dust size to kind of 30 feet or 10 meters in diameter. And essentially they're broken up asteroids, smaller asteroids. They have the same composition as we've stated about asteroid, and they're named on their position relative to Earth. And sometimes people are confused by these words, so it's important to kind of think about these words. So a meteoroid is when it's still in space, these objects less than 10 meters in diameter. And once it enters Earth's atmosphere, we change that name to a meteor. So a meteor, when it makes contact with our atmosphere, and we often call these shooting stars when they burn up in our atmosphere. So that's a meteor. If they strike the surface and only then make contact with the surface, we call them meteorites. So meteorites are the actual material once it hits, terra firma, the ground, and people can find them, take them to their local museum and say, hey, I found a meteorite. How much is it worth? Do remember those different terms for these meteoroids, depending on whether they're in space, traveling through the atmosphere, or have already struck the ground. What about comets? Often compared to large, dirty snowballs, essentially. It's kind of a good analogy because they are basically frozen gases, essentially frozen material, ice, but with small kind of bits of gravel material, if you will, embedded in it. So composition, frozen gases, water, ammonia, methane, carbon dioxide, carbon monoxide. Small pieces of rocky metallic materials are usually embedded within it. The frozen gases vaporize when near the sun. So they often have very, very eccentric orbits where they start off. They thought to come from way out in the Kuiper belt, Oort cloud, way out past Neptune. The orbits of these comets take them to the outer, very cold outer solar system. But these ones with eccentric orbits do come into the inner part of the solar system. And that's when these frozen gases are vaporized when they're near the sun. They produce a glowing head called the coma, you can see in a photograph top right, and some may develop a tail that points away from the sun. You see here. So here the orientation of the comet's tail as it orbits the sun. And here you'll see as this comet orbits the sun, you'll see the coma, the glowing head, but also this tail, and actually two tails sometimes occur. Here the tail composed of dust and the other one ionized gases. So you'll see these tails don't kind of follow the path, if you will, trailing behind as you might expect of the comet. They actually go kind of at an angle away from the sun. That's because the sun is emanating the kind of the solar wind, ionized material coming out from the sun constantly, and solar radiation, and that will cause these tails to be dragged out, with that solar wind away perpendicular to the sun, and that's why you see these tails going away from that. But sometimes it does it at slightly different angles because of the momentum as well of the comet, and the tail composed of dust here, and then another one of the ionized gases. So their origin, not well known. They form at great distance from the sun. We know that most reside in the outer solar system in the Kuiper belt and Oort cloud, but sometimes during their orbit they come into some of them into the inner solar system, and could then potentially be a hazard to us. Most famous short period comet is the famous Halley's Comet or Halley's Comet. It has a 76-year orbital period. It's kind of this irregular shaped comet, around about 16 kilometers long by about 8 kilometers wide. And it's actually the only comet which you could potentially, large comet which you could potentially, which is visible with the naked eye, you can see once or possibly even twice in your lifetime. I saw it when I was a child back in 1986, a long time ago now. I remember looking up in the sky vividly and seeing the tail. It's really obvious. So hopefully you guys, 1986, add another 76 years. Haven't done the math yet, but hopefully you guys will get to see the next one when it comes around, because it is really actually pretty spectacular to look up in the night sky. Hopefully it's a clear night. It was for me back in 1986, and yeah, it's a sight to behold. So that's Halley's Comet, the famous one. It was discovered many centuries ago, actually. Okay, so what about do these events happen? Do they strike Earth? We have these things orbiting the sun. Some of them come into the orbit of the Earth and the inner solar system. Have we seen any? Well, I mentioned the comet Shoemaker-Levy back in 1994. It struck Jupiter, and this comet basically started to orbit Jupiter from the huge gravitational pull. Basically, it was trapped in Jupiter's orbit, kind of span around a few times, and as it did, broke up into smaller pieces, and then finally impacted into the upper atmosphere of Jupiter. And here you can see impact events. And basically what happened, these broken pieces came one after the other, wham, 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 and caused these, you can see 1, 2, 3 on this image of impacts into the atmosphere of Jupiter. Remember, Jupiter is a huge planet, so each one of these kind of circles of light is the size of Earth almost. And here you can see in the black images here again in this image where the bottom right photo where the impacts happened in the atmosphere of Jupiter. And this was, we knew it was going to happen back in 1994. We could see it was about to happen, and everyone's telescopes was looking at it, were focused on it, and we saw an impact event in real time. So we know it does happen. These things do happen, and it's happened in recent years. Okay, closer to home, the moon. Do we see this kind of ones where these broken up comets and asteroids where they come in for one after the other in quick succession? Yeah, you can see evidence of those. It's crater chain on the moon. You can see them as they came down and struck the moon, one out of these broken pieces, one after the other. What about the Earth? This is the hazard where people live. So, well, the last big event of some size to strike Earth happened over 100 years ago now, and it's called the Tunguska event of 1908. It happened in Siberia, and I'll tell you a few things about it. Here you can see these trees in the background sort of snapped and felled over, sort of broken over in Siberia. So what happened here? It was an asteroid airburst. It actually exploded in the air around about 3 to 6 miles up. We think the asteroid was of a size, the object, 200 to 600 feet in diameter, of an explosive force of 15 megatons of TNT. So that's 15 megatons. Put that into context, that's about 1,000 times greater than the Hiroshima bomb, atomic bomb of World War II. 1,000 times greater. Put that in perspective, 15 megatons. The largest H-bomb explosion was the test at Bikini Atoll in 1954. That was 58 megatons. So this is 15 megatons. Anyway, felled trees, 80 million trees over 130 square miles. No fatalities. Fortunately, this happened in the middle of middle northern Arctic Siberia, and there was no one there in this area, so there were no fatalities for this event, which was obviously fortunate. Um, all right, so we know events can, within the last 100 years, large events can happen. If that Tunguska event had struck a city, for example, it would be what we call a city killer, a city destroyer. So if it happened in the US, in central cities like Philadelphia or Manhattan, yeah, it would have destroyed a city. But the chances of that happening are pretty small. Okay, what about evidence of craters? Fortunately, well, just going back to that last point, we live on the blue planet. 70% of the Earth's surface is covered by water. So most of these impact events we think of the Tunguska style, which we now think happen about every 100 years, on remote places like Siberia, northern Canada, or the ocean, so that they they don't cause any damage as such. Okay, what about actual craters? Are there any craters? There's all the craters on the moon. Do we have craters on Earth? Well, the most famous one, and probably the best one, is Meteor Crater in Arizona. I don't know if any of you guys have been there. Do you have a visitor center close by to it to kind of go and look at it if you ever out that way? So this cavity is about 3/4 of a mile across, 560 feet deep. It occurred a long time ago, around about 50,000 years ago, during kind of the early stages of the last ice age. But this area was actually much the same, because the southern part of the state, so it was actually much the same as we see now. It was still, we think, kind of a desert, arid environment at that time, 50,000 years ago. There's lots of evidence for it. There's very highly fractured bedrock beneath it. When you look at the geology below there, you see upturned crater rims, etc. And there's lots of other evidence which we'll go through in a second, a few slides time, about of an impact. Okay, so there's a meteor crater. Very few other examples of craters, actual craters you can see as a crater on the Earth. Why? Well, it goes back to what I said earlier. It's weathering and erosion. Why has it not happened in Arizona? Well, it's a desert. It doesn't rain. Very little. So very slow rates of, say, weathering or erosion. Therefore, it's still preserved 50,000 years ago. So we define names like meteor as a meteorite. So when they strike the ground, here's an iron meteorite found near meteor crater. So we think, a chunk of that larger meteorite which struck the planet. We think the object, by the way, people have calculated it's probably about 160 feet across, the incoming asteroid at the time, and explosive force of around about 10 megatons. Okay, so this shows on the left kind of just an impact event, what happens. There's that word I mentioned earlier, sort of catch-all word for all kind of objects coming in, bolide. But then we've said we can call it asteroids, they're rocky material, comets if they're icy material, large objects, both of them, or meteorites, which are smaller, much smaller incoming kind of rocky material, less than 10 meters generally. Extraterrestrial bodies move faster than a speeding bullet, generally around about sort of the low end of the scale, 20 kilometers per second. And they explode and produce huge craters, and ejector goes out when they impact. They can produce two different types of crater, either just a simple crater, like I've shown at the top, a simple depression of a crater rim, or sometimes once it's kind of impacts and the way the ejectors then kind of bounces back, if you will, they often form what's called, or sometimes form, a complex crater, and that has this central peak in the middle. Example of a simple crater is meteor crater in Arizona. So it's bowl shaped, around about a kilometer in size, has that crater rim, etc. It was first identified, by the way, in the 1920s. Prior to then, a lot of these things were thought to be volcanic craters, and then they started to see the evidence of this being an impact event. On the moon, you can see an example here. It's got a peak in the middle, a complex crater, King crater. And some facts and figures about that. Yeah. Okay, so this diagram shows kind of what happens when these impacts occur. So you have a central region where basically where the center of the crater would be, and everything. And we're talking, things moving at 20 kilometers per second. They can be, a kilometer in diameter, the big things, or even several hundred meters in diameter, and they will vaporize. Essentially, they would atomize, vaporize things in the close vicinity. Temperatures are up to up to 10,000 to 30,000 degrees Celsius. And then you have melting of the rocks and partial melting as you go outwards, and then deformation as well of the rocks further out. So different zones of deformation as you go with distance from the impact location. So how can you tell you've got one? How can you tell this is a former site of an impact event? And so you look for various lines of evidence. You look for metamorphism, which is where basically rocks are deformed into something else, if you will, and something called shock metamorphism. And especially you look for things like ejecta, material thrown out, often in these rays, in lines, and the material often decreases with distance as you sort of size, or it does with distance from the impact. So you have proximal material, large scale, larger ejecta fragments, and then these fragments get smaller and smaller, so they're just kind of sand grain size and smaller, but you can still see them on a microscope further away from the object. Some evidence, so some famous ones of impacts on Earth, well, one on the Moon as well, to Macaris. But here, first on the top right, is in Canada, in northern Quebec, the Manicouagan crater. And if you looked at an atlas now or a map of northern Quebec, you would see actually a lake with this. This has all been infilled, this depression around it, with a lake, a modern day lake formed in this circular pattern here. It happened a long time ago. It's 100 kilometers across. This was a large impact. So the crater it's around about 100 kilometers across, and it happened 200 million years ago, and it's thought to be associated with a mass extinction event, the late Triassic, or it's called the late Triassic mass extinction event. Because when you think about when these huge impacts occur, they throw up huge quantities of material into the atmosphere, and essentially can cause, like a nuclear winter, essentially after a nuclear bomb, but that can last months, and that can actually shut down photosynthesis, and then that happens, plants die, green plants, photosynthesizing plants, and that affects the whole food web, food chain, beyond that. Chicxulub crater, actually before I mentioned that one, what about the one on the bottom right? It's a geologic map, but it shows the pattern of these pink rocks and the beige ones in the middle, a circular pattern, and this is the Reese, or the Reese-Kessel impact location, impact event, which happened around about 15 million years ago in the Miocene, and that is around about 20 kilometers in diameter, and it's located in Germany, in southern Germany, in the western part of Bavaria. You can still see the crater on this one. It's one of the rare ones you can. There is a crater rim on it, and it's about 400 feet deep from the kind of the bottom of the depression to the top. It's actually got ancient, old, within that crater. There's some very, very old medieval towns in this part of Germany, and kind of built within a crater, which is kind of cool, I think. Its explosive force around about 2 times the Hiroshima bomb, we think, when it came down. Bottom left, this is the famous Chicxulub crater of the Yucatan Peninsula in Mexico, the Gulf of Mexico. And it's around about 180 kilometers in diameter. It was actually discovered in, we'll come back to more details on this, because this is the one where the dinosaurs go extinct from this event, we think now. So yeah, I'll just mention it's a large crater at this point, and then we'll come back to some more facts, more info on the Chicxulub crater. Okay, so other types of evidence. You have your craters. What about if you go out from the crater? You have macroscopic evidence, things you can see with the naked eye. So you can get these what's called swavite melt rock. You can have these tektite buttons, essentially melt rock, which go through melted droplets of rocks, which fly through the air at incredible fast speed, and they produce this shape as they fly through the air, and then you can then later find them, and you get lots of deformation of the rocks where that large impact took place as well. Impact breccia, you can see in these rock cores, you can get these things called shatter cones, again, from the massive impact and pressure on the rocks below when it happens. These glass spherules being formed as well from impact, essentially things being melted. Microscopic evidence, and this is actually important evidence, is something called shocked quartz. Quartz is a really hard grain. You see quartz on a beach, a sandy beach often. It's basically grains of the mineral quartz. Quartz is a very hard mineral. It's not normally got any fractures in it. But there's two ways to fracture a grain of quartz. One is a nuclear explosion, will do it, and the other is an asteroid impact. They're the only two ways you can really produce these things. It needs that kind of energy release. And here you can see on the bottom right and the bottom left, these shocked grain, quartz grains, and these have been found in huge quantities around impact events, and then becoming less and less concentrations away from the impact event as well, which helps you actually locate the impact event. Okay, geochemical evidence. Iridium. This brings us back to the story about Chicxulub crater, which happened 65 million years ago, and we know now pretty much, or we think that it's associated with the demise, the extinction of dinosaurs, most non-avian dinosaurs. Anyway, iridium. Okay, so iridium is a very rare element, extremely rare on Earth. We're talking so rare it's hardly detectable, even with modern, devices in the lab. It's generally we think something like 1 to 2 billionths of a gram of normal kind of rocks have iridium in. So it's a rare metal, a bit like platinum. But this location, occasionally you can have these what are called iridium anomalies, and there's a famous one we're going to talk about here, and associated, which has been dated to this iridium anomaly all around the world actually, in a clay layer, to 65 million years ago. And this iridium anomaly here is something, something like 600 times the more iridium in this peak of iridium shown in the black line in this graph at this depth. In this case, a location in Italy. So I'll talk you through it. So here, these two geologists, father and son geologists. The father was Louis, son Walter Alvarez. Back in 1977, the American geologists, and they were working in Italy. Back in 1977, geochemists, both of them, and they found this layer, an iridium anomaly. Thank you. And they measured the amount of iridium in there, and it was, large amounts. The only place you get large concentrations of iridium, you don't get it on Earth, is extraterrestrial objects. You only get them on fragments of asteroid and comets. You do not get them on planetary Earth rocks. So this, when they saw a spike, both of these geologists said, "Hey, something going on here. Is this a sign of an impact event?" The rocks above and below had very, very low amounts of iridium, and these rocks also, paleontologically, as far as life goes, above this point, no dinosaur bones, and a whole host of other things. Below this point, we have the fossils of various organisms before they went extinct at the 65 million year point. So at 65 million years ago, the dinosaurs went extinct. In fact, 80% of species on our planet went extinct. No one quite knew the reason for then up until this point. We thought volcanic eruptions, we thought climate change, which were all valid and are good reasons and do happen at other stages of Earth's history, but they weren't quite sure still. And then they discovered this, the Alvarez father and son teams discovered this, and they started looking at iridium records, dating it all around the world, and saw something was going on. There was an impact event somewhere on planet Earth around about 65 million years ago. They didn't know where at that point. It took later till 1990. They published their work in 1980 though, and to say that this is the reason. It was an impact event that caused the extinction, the mass extinction, 65 million years ago. The actual crater, it took another 10 years to actually discover that. And that was found by, had been looked at but overlooked in the Yucatan, but then it was through further sampling, they confirmed it was the Chicxulub crater on the Yucatan. And only recently, 2016, 2020, studies have really given much more evidence to show locally evidence of an impact event there of a huge size. So we think, the Chicxulub crater was caused by an object, by the way, around about 7 miles or 6 miles in diameter, so 8 and 9 kilometers in diameter. A huge impact. So asteroids and mass extinctions. Yes, we think they do cause mass extinction events. So there's been some big asteroid, some big extinction events going through Earth's history. There's 1, 2, 3, 5 main ones, and actually you can add to another one. We think modern day extinction due to human activity is what we call the Anthropocene extinction event. But let's take that one out of the equation for now. For modern day climate change and habitat loss. Here we have one around the KT boundary, the Cretaceous Tertiary, and they call it the KT, the letter K hyphen letter T, because the shortened version for Cretaceous is K, and then we have that's the Cretaceous period of Earth's history. Then it moves into the Tertiary period, which is T, so hence KT boundary. Anyway, this is the amount of species that went extinct, or families in this case, so larger groups of animals. And you can see there's a KT boundary. There's one in the late Triassic. That's the one 200 million years ago, possibly associated with the Manicouagan impact event in Canada. Then actually, it's not shown here, but in terms of the number of species, not families, that went extinct, this is the biggest one, the Permian Triassic. And that was a combination of things, including climate change at the time and supervolcanic eruption. Then there were other ones we think are more to do with climate change, late Devonian and late Ordovician. But impacts, definitely, certainly the last two, have a strong influence, if not the key reason for these impact events. So here we're talking every sort of 100, 200 million years, we have these very large impact events, possibly associated with, like I say, mass extinctions associated with impacts. So the Chicxulub crater, 65 million years ago. Here's the iridium anomaly in this clay. It's been found worldwide. Here we now know where the crater is, in the Yucatan Peninsula kind of part, under the sea, in the Gulf of Mexico part on land. Discovered originally from petroleum geologists in the area. Then later, around about 1990, they re-looked at the area and found evidence for an impact. Other craters now completely buried under the ground. You won't see them on the surface, but there's a famous one now, or an important one, in Chesapeake Bay on the east coast of America. So here, this here highlighted here with in the red here, the impact site at the mouth of the Chesapeake Bay happened 35 million years ago, and a huge impact event that happened back then. It's actually, we think, what actually caused the draining of the Susquehanna River, which is the main river into the Chesapeake, to follow its path here. It was discovered, this is the Chesapeake crater in cross section, so lots and lots of boreholes, lots and lots of geophysical kind of exploration to get this kind of image of what's going on underground. And you can here see it is a complex crater, it has a peak in the middle, and there's the crater rims, lots of fault breccia, lots of deformation, and impact breccia, and it's a definite crater. You can't really say anything else about it. It's an impact crater, which happened 35 million years ago. All right, almost finished. So what happens when these things, we know these things happen. We know that they're pretty rare as far as these big events, these kind of game changer events for civilizations or for evolution, fortunately, like very rare. We're talking on tens or even millions of years, hundreds of millions of years time scale, but they do happen. So what happens when it takes place? Here, this taken from the NASA website. Here, 15 megaton impacts, Tunguska class. These are the ones I mentioned earlier, so kind of city killers. Average interval, around about every 100 years. Most of them, though, when they happen, enter the ocean. Could be Antarctica, could be northern Siberia. So fortunately, no one's at risk. Larger ones, 10,000 megaton impact events. These could essentially destroy a small country around about every 100,000 years, we think. Global catastrophes, we're talking about over 1 million megatons of explosive force. Very rare, maybe every 1 million years. Still, it's every million years, but it happens through, it affects evolution. So on this chart, it shows there's 1 million years, but if you go to the far right, the KT type one, the 65 million year one, they only happen, we think, every 100 to every 200 million years. So, fortunately. Okay, so what can we do about it? We know they happen. We know they're incredibly rare. So don't get worried, folks. Incredibly rare. But they do happen. So do scientists take it seriously? Yes, they do, especially NASA. That they started a program called the Space Guard Survey, which was set up way back in 1992, and its target was to discover and track at least 90% of near-Earth asteroids, NEAs, with a diameter greater than 1 kilometer, and to do that by 2012. They did that. They succeeded. We now know, because the number isn't going up, it's leveled off around about 900. We have about 900 objects which we can track. We know they're NEAs. They do have an eccentric orbit, and we track them. We can see them going around. So the key thing is to really identify and track, and then assess the risk and calculate whether or not there's a very small probability of these, colliding with Earth. Okay, moving on to 2021. So here, taken from the NASA website, August 20th, 2021. It shows you, and you can dip into this website any point and have a look here, and it shows you the number of NEAs identified. And here, there's ones at 900 over 1 kilometer in diameter, around about 900. But they're now also tracking ones which are over this threshold of around about 140 meters in diameter, which are potentially large hazard, very hazardous. Something we could possibly hope to do something about, because they are hazardous on a big scale. And something like 25,000 of them. I mean, 25,000 of these smaller NEAs or NEAs in total have been identified now. What can we do to finish off? Okay, we're identifying them, we're tracking them, we know the probability of them striking Earth. What can we do? Well, I'll just say to one point on here, if you don't have Bruce Willis at hand to send him up there, like in the movie Armageddon, the main thing we think in the future, once the technology is there, is to actually change the orbit just by a tiny fraction of these asteroids, but many years, if not decades in advance. So we're talking maybe several orbits of the sun, many orbits of the sun, but just as they go around, getting a spacecraft up there, landing it on that asteroid, setting off an explosion kind of remotely, and that will not break it up, but it will slightly deflect its path just by a fraction of a degree angle, and that's all you need for it to then not strike Earth 20 years later. So that's the thing. Can we land crafts on asteroids? Yes, we actually did. Back in 2001, Eros. There's actually a photo of Eros earlier in this slide deck, and that happened in 2001. It was a near-Earth asteroid rendezvous project, or NEAR project, and they landed a craft actually on and took photos on Eros back in 2001. All right, so before there's the end, but I should have actually, last slide, mentioned something which you may have heard on the news about one more famous asteroid. Came to the news back in 2001. It's called Apophis, Apophis, Apophis. That was discovered in 2001, and it was actually very worrying to a lot of people. I don't know if you remember it in the news, because they calculated back then there was a 2.7%. It's only small, but still no, big enough. 2.7% chance of impact with the Earth in 2029. And this object is big, Apophis. It's 370 meters, or over 1,000 feet in diameter, 1,200 feet in diameter. And they say there might be an impact in 2029. Very small chance, but still, a couple of percent. Well, the good news is 2021 is NASA now says there's no threat. They've recalculated, and there's no threat of an impact, certainly in at least 100 years of Apophis. So we can now discount Apophis as a potential, hazard, we think. All right, I'll leave it there. There's an artist's impression of the Chicxulub asteroid coming in, causing in this case, a mega tsunami, which is yet another thing actually I haven't mentioned. They would have caused a huge mega tsunami in the Gulf of Mexico, which would have traveled up the Mississippi Valley, across the coastal plains of that area, and caused a lot of destruction just in itself. All right, that's it, and I'll see you next time, guys. Thanks.